Thanks, Noah. That was a great introduction. Being a climate scientist is an emotionally stressful job. There's a lot of bad news that one needs to communicate. But I want to start today by thanking the organizers, and especially for putting the climate talk on today, because today is the day that the Paris Climate Agreement comes into action. So it's been ratified, and actually starting today there's legally binding commitments in terms of global climate. So there is sparks of good news. I'm going to talk about paleoclimate today. I'm a paleoclimatologist. I use primarily tree rings to study the climate of the past. And Noah has given a good introduction of why we study the climate of the past, primarily because we want to put ongoing climate change in a longer-term context, and we want to help improve climate models to see how much of what we're witnessing at the moment is due to anthropogenic or man-made emissions, and how much of that is due to natural variability in the climate system, and what are the drivers of natural variability in climate. I think most of you are probably familiar with the graph here, which shows a 800,000 year long record of carbon dioxide in the atmosphere and of temperature in the atmosphere. It's derived from an ice core in Antarctica. It shows that the global temperatures follow the amount of carbon dioxide in the atmosphere closely. Have been doing that over the last 800,000 years. I would like to point out this axis to you. So the amount of carbon dioxide in the atmosphere over the last 800,000 years has been fluctuating pretty steadily between about 180 parts per million and about 280 parts per million. If you paid attention to Noah's talk, you know that right now we're above 400 ppm. I want to point out this y-axis doesn't go to 400. It goes to 300, which is the CO2 level when the Cubs last won the World Series. So ice cores is one way to look at the climate of the past. There's many, we call them climate proxies, so indirect ways of studying the past climate that we can use. Stalagmites, lake sediments, tree rings, and so forth. And they all have their advantages and disadvantages. When we're talking about climate extremes, and also the impact of climate extremes on human societies, there's quite a few advantages to studying tree rings. One of them is the time period that we can cover with tree ring data. Is approximately the last 2,000 years. So we don't have 800,000-year-old trees, but we have fairly old trees. And what we do when I talk about tree ring data is, so literally we measure the width of the rings in a tree, and then we find the patterns in that ring width. We relate the patterns in the ring width of a tree. So I'm imagining everyone has looked at the rings in trees when they were a child. We relate the patterns in those trees to climate. That's how we can reconstruct the climate back in time. But we can also relate the patterns in the trees, in the living trees, to the patterns that we find in dead trees, but also in wood from historical buildings, in archaeological wood, in wood that's been found in bogs and lakes and so forth. So that allows us to basically patch together these patterns and go further back in time than just the age of the living trees. So, as I mentioned before, mostly that's being done over the last 2,000 years, which corresponds to the period that's best documented in terms of human society and human history, and that's also most relevant to human history. The pictures below here, this time series, is from a study that I've done with my colleagues Ulf Buntgen, where we basically patched together wood from Central Europe to look at the influence of climate variability on the fall of the Roman Empire. So I won't talk about that. You can read it if you're interested in that. Another advantage of tree rings compared to other climate proxies is they form a ring each and every year. So we can have a climate data point every year, which is a big advantage if you're looking at climate extremes. If you only have a data point every 10 years or every century, as is the case for many other proxies, you can't really look at these extremes that happen on much shorter timescales. I'll talk about 3 examples. I hope I have time for that today. I'll start with talking about hurricanes, and then in the Caribbean, and then I'll move over to California. I'll talk a little bit about the California drought and also wildfires in California. And so I'll show how we've used tree rings to study these 3 climate extremes over the last 500 years, more or less. So hurricanes in the Caribbean region, a big climate extreme that has far-reaching economic and societal effects, I think. Saul will talk a little more about them in the next talk. Just think about Hurricane Matthew that happened earlier this year. So have a very big effect on society. It's important for us to understand how hurricanes are going to change under future climate change. And in general, generally speaking, and globally speaking, most climate models agree that in the coming century, hurricanes will become less frequent, but more intense. So there'll be less hurricanes, but they're going to be more intense and more destructive. That is globally speaking, though there's a lot of uncertainties around that, and especially when you start looking at individual basins, at specific regions. And so for instance, for the North Atlantic basin, the main source of uncertainty is that we don't understand well how the hurricanes or tropical storms or tropical cyclones react to changes in the radiative forcing, so changes in the amount of radiation that reaches the Earth's surface. We don't have a good enough understanding of that because we don't have enough replication of these types of extreme events. So the amount of carbon dioxide that's in the atmosphere is a big driver, or a big changes the amount of radiation that reaches the atmosphere. If we want to better understand how hurricanes react to that radiative change, we can go further back in time and see whether there were other periods of time when there was a big change in the amount of radiation that reached the Earth's surface, and how hurricanes have reacted to that. So the best known period of time that we know of in the recent past when there was a big change in the amount of radiation that reached the Earth's surface was the Maunder Minimum. So this was a period of about 70 years in the late 17th century when we know there was a severe reduction in the amount of energy that the sun sent to the Earth. And that resulted in a period called the Little Ice Age, or it was, I need to be careful what I say here, but there was a strong relation between the Maunder Minimum, so a minimum in the amount of energy that the sun sent to the Earth, and the global temperatures on Earth at that time. So for instance, this painting was painted in 1683, right in the middle of the Maunder Minimum, and it depicts the River Thames in London that was frozen over, and they were having a 3-month-long frost fair on the River Thames. That doesn't really happen anymore nowadays. So we came up with the idea that if we want to see what hurricanes, if we were able to reconstruct hurricane activity back to that period, it would teach us something about how hurricanes react to radiative forcing. And the idea of this study came about when I was at a tree ring conference, and one of my colleagues, Marta Dominguez, she's an archaeologist. She uses tree rings to date archaeological material, and she is specialized in shipwrecks. So if you think, I have a cool job as a tree scientist, she has an even cooler job. So she dives to shipwrecks, pulls out the wood, dates the wood, finds out what types of wood, when those ships were built, what type of forest management, where the wood came from. Anyway, she was talking about her exciting research. And I was thinking about hurricanes and tropical storms. And so we, in that discussion, we decided to see whether we could use documentary shipwreck data, so not the wood, but the documents that dated when ships wrecked, whether we could use these as a proxy of when hurricanes happened in the Caribbean. And so we looked at the Spanish records. The Spanish were the first to do the transatlantic voyage. And they would, starting in 1492 with Columbus, they would sail to the Caribbean, load up on gold, and then sail back. And that was their, the gold that they got from the Americas was their, that really allowed them to dominate European politics and the European economy at that point, because they were the only ones who actually had gold. So for them, this whole shipping business to and from the Americas was extremely important resource, and they kept very well track of every single ship that they sent out, every single ship that wrecked, where it wrecked, when it wrecked, why it wrecked. So there's very good records of how many Spanish ships wrecked in the Caribbean since 1492. So we made a time series of those shipwrecks. This is what it looks like. It starts in 1495 when the first ship wrecked, and we ended it in 1825. After 1825, there was a lot of technological advances, a lot of competition from other countries as well. So the record became less reliable afterwards. I won't go into much detail, but obviously there's a lot of assumptions that we're making here when building this time series of shipwrecks. And the biggest one probably is that not all ships wrecked because of storms. There were a lot of other reasons why ships wrecked. And so normally what we do is we take our proxy record and we take the instrumental record and we compare it to. And we see whether what we assume are hurricanes actually correspond to hurricanes over the instrumental data. But the instrumental data only start in 1850 in terms of hurricanes in the Caribbean. So we only systematically and reliably started recording how many storms happened every year at about 1850. So we weren't really able to do that calibration because there was no period of overlap. That's where the tree rings come in. So in order to make that happen, we took another colleague of mine on board, Grant Harley, who's at the University of Southern Mississippi. And he has a tree ring record from the Florida Keys. Again, he has a pretty nice job, goes to the Florida Keys, samples a bunch of trees there. And so they're pine trees, and when a hurricane hits the Florida Keys, the pine trees lose all their needles, they lose a lot of branches, and they grow much less in the years following a hurricane than they grow in normal years. And that's reflected in the tree rings. You see these periods when there's much narrower rings, much less growth that you can match up across different trees, and then you can correlate that or look at whether those years with reduced growth correspond to hurricane years. So combining the tree ring data and the shipwreck data, we were able to develop a record, a proxy for hurricane activity back to 1500. This is now at a decadal scale. And when we put that time series together, we noticed this 60-year period when there was remarkably actually a 75% reduction in the amount of ships that wrecked in the Caribbean. And if you pay attention to the timing of this 70-year reduction, it overlaps year to year with the Maunder Minimum. So this now is the amount of, a proxy of the amount of sun that reached the Earth's surface back to the year, I think 1600. And so you can see that this reduction in amount of shipwrecks, and so assumedly the amount of hurricanes, corresponds in time to this reduction in the amount of the energy from the sun. These are fully independent data sets, obviously, and here are some more independent data sets, other proxies that record the temperature of the ocean in the North Atlantic back in time, 4 different records, and they all show during the Maunder Minimum that global temperatures were cooler, but also ocean temperatures in the North Atlantic basin were cooler, which is a potential explanation of why there would be a reduction in the number of hurricanes. Okay, now moving to the West Coast into California, I can be short about this next couple of slides because Noah already gave a nice introduction. This is the condition of the California drought as of last week, with about 20% of California still in exceptional drought. Northern California is doing better nowadays. This is this original slide before a graphic designer worked on it. There are nice y-axes. So as Noah mentioned, the drought is strongly driven by rising temperatures. This lower figure is from a paper by my colleagues Zane Griffin and Kevin Anchikaitis, who used trewings to reconstruct the California drought back in time, back over the last 1,200 years. And they found the same thing. This was in 2014, so only in the middle of the drought, really, and they showed that the 2014 drought was the most severe over the last 1,200 years. The precipitation was not the most severe, but the temperatures were really the ones that were driving this. Also mentioned by Noah is that one of the, at least the most visual ways of looking at the California drought is looking at snowpack in the Sierra Nevada. The satellite image on the left shows a pretty average year, the snow condition in the Sierra Nevada over an average year in 2010. So typically, snowpack is looked at on April 1st. April 1st or right around then. It's assumed at that point of year most of the snow has fallen but hasn't melted yet. 2015, this is what the snowpack looked like. So a far below average snowpack here. I'm talking about snowpack, but another way of looking at it is the snow water equivalent, or SWE. So it's basically the amount of water that's available in one unit of snow. So on April 1st, 2015, the data come out that said that the 2015 SWE values were at 5% of average over the period that snowpack has been measured since 1930 to the present. And when those data came out, we realized, my group and I realized, that we had the trewing data at hand to put that number in a much longer context. So what we did is we went ahead and reconstructed that snowpack, Sierra Nevada snowpack, back over the last 500 years. We used a combination of precipitation-sensitive trees, the blue oaks from the Central Valley, some of the most rainfall-sensitive trees on Earth, with a trewing-based temperature reconstruction from the region. We combined the two. We calibrated against the snowpack, reconstructed. So this is now the reconstruction. The red dotted line is the year 2015, and you can see that 2015 is the lowest snowpack, not just over the last 80 years, but over the last 500 years. Given the relevance of snowpack to the California economy, this was big news. The media hit us hard. in a good way. So I want to just show this slide from the New York Times. And I wanted to actually show you the actual paper, but I forgot it. That the top half of the page is reports on our study that the snowpack is in a 500-year low. The bottom half is what I would like to point you at. The sideline here is that talks about, this was published in September last year, that 3 major wildfires were burning in California. That's not a coincidence, obviously. Drought in California doesn't only influence human societies, but also has a very strong impact on ecosystems in the region. And so that's what my last example will be about. It's about wildfires, not strictly speaking climate, but it's closely related. So in another study that's actually coming out week after next, we collected data from 29 sites throughout the Sierra Nevada, so over 600 kilometers spanning from north of Lake Tahoe all the way to Sequoia Skin Canyon. 2,000 samples with more than with almost 20,000 fire scars in them. So a quick introduction of how we can use tree rings to also reconstruct past fire history is that when a fire hits a forest, and I'm talking about low intensity fires here, boing, that was not so low intensity, fires that are not crown fires, so they not the kind of wildfires that we see nowadays, but low intensity fires, when they hit a forest, they wound a tree without killing it. And so it's like if you get a fire wound yourself, that part of your skin is going to be most sensitive. If a number of years later another fire comes, it's going to scar, it's going to leave the biggest scar in the same spot. So it's the same with trees. The part of the tree that was originally wounded by a fire is going to be wounded again by subsequent fires. And so all of these layers, has anyone seen this in real life? Because it's really phenomenal. And once you know what you're looking at, they're everywhere in the Sierra Nevada. So these are all subsequent layers of fire that were left by subsequent fires. So we found trees with 30, 35 subsequent fire scars in them. And so when you take a sample here and you sand it, this is what it looks like. And so you can actually, by tree ring dating, you can see the scars here. And by tree ring dating, you can date the year of when each of these fires happened. You can, in many cases, you can actually even see what season that fire happened at. So this is a typical sample, and as you can see, fires happened prior to 1900 about every 5 to 12 years. Every site was hit about every 5 to 12 years by a wildfire in the Sierra Nevada. Now we added up those almost 2,000 samples from throughout the Sierra Nevada into one big fire index, Sierra Nevada Fire Index. That again starts right around 1500. This is an annual fire index. You can see there's some extreme years like 1829 when 24 of the 29 sites all burned. It was a huge fire year in the Sierra Nevada. And what we found when you can compare this to a drought record, unsurprisingly, this is now a correlation map that shows the correlation between that fire record that I just showed you and independent gridded drought reconstruction. You can see that dry years in California result in big fire years in California. Not that surprising as a result, not really anything worth spending 2 years of your life on, not really anything that's going to get you in PNAS. What we found, though, is we saw more in the fire record than just the interannual variability. So if you look at, this is again that fire record, apart from the year-to-year variability, we found 3 distinct shifts, longer-term shifts in the fire record. First one around 1775, before which from 1600 to 1775, fires were fairly steady in terms of size and synchronicity. After 70-75, you get more synchronous fires and larger fires, and then after 1865, the level of fires go back to what they were before 70-75, and then after 1900, you get a very severe reduction in the number of fires. These shifts, these three shifts, so the 1775 one, the 1865 one, and 1905 one, they don't correspond to, there's no shifts at the same time in neither the temperature record nor the drought record. So those shifts are not driven by shifts in the climate. There's more shifts over the 20th century, but I'll leave those up for the time being. So if not climate, what is driving these large decadal scale shifts in the fire regime of the Sierra Nevada? Well, we'll start with the most recent one, 1904, 1905. That one was pretty well known already. We call it the Smokey the Bear effect. Around 1900 is when the fire suppression started kicking in the Sierra Nevadas, and we were quite efficient at it. So you can see the very severe reduction in number of fires. That's man-made. That's because we were putting out those fires. I'll make one comment. If you think of during this whole period, fires happening every 5 to 12 years on a certain site, and then Smokey the Bear comes in and you get 100 years of no fires, virtually no fires, you can only imagine what that does to the fuel load, right? So those low intensity frequent fires, they would kill the grasses, kill the small trees, but wouldn't touch the big trees, or not kill them at least. If you don't do that for 100 years, and then a fire hits, it just explodes. That's what we're seeing now. What we're seeing now is not just temperatures rising, it's the fact that we've been putting out fires for 100 years and just letting those fuels build up and build up and build up. But that's another story. The previous one, the 1865 shift in the wildfire regime, that came right after the gold rush. So around 1849, gold was discovered in California, huge influx of European immigrants that cut down a lot of trees to build the railroads and to use in the mines, brought in a lot of cattle that ate all of that grazed and ate a lot of those fuels. And so it's a land use shift that really changed the fuel and forest conditions. The first shift around 1775 or 1776 was probably the most surprising one to us. And our hypothesis is that, well, we know it happened shortly after the mission establishment. So the missions in California were established in 1769, the first one. And so prior to that, the indigenous population, Native American population, they did a lot of burning. But they did small-scale burning. So they would burn for hunting and for preparation of agricultural lands. So they would burn, but not large areas. And so they would create a patchwork. They would burn some areas at some point in time, some other areas at other points in time, which stops the fires from spreading over large areas. With the establishment of the missions in 1769, the missionaries brought, two things happened. One, they brought, as you probably know better than me, brought a lot of diseases with them, and the Native American population was decimated. And two, they also established, they had some policies that would not allow the Native Americans to burn. So they had strict policies that Native Americans were not allowed to burn the land. And as a result, because you lose that patchwork of small burns, you get larger and more simultaneous burns during the period after the mission establishment. I'm not showing this here by lack of time, but this is also the period when the connection between drought and fire is strongest during this period. So when the human input is smallest, the connection between wildfire and climate is strongest. And I want to end there. It's a semi-positive note in that there's not much we can do in the short term in terms of the temperatures rising in California, but there is something we can do about their influence on wildfires. If we can get back to a more small-scale burning landscape, then we can at least reduce the influence of climate on wildfires. So with that, I'd like to thank you for your attention. I'd like to thank all of my students and collaborators who've put blood, sweat, and tears into this. So if you want to learn more about them, visit our website.